Hello and welcome to our tutorial One Machine Model. So what we are going to do is to model a one machine model in Anylogic. The important information is on this slide. If you try or if you need to get in contact with me, write me an email a.hubel@roch.nl. So the software we are going to use is Anylogic in its latest version 8.6.0, and we're using the PLE version. So this is available for all Windows systems and as well for the beautiful Mac systems. So what we're going to do is we're going to model a one machine model. You can see here the beautiful model. We have the two constraints, the boundary lines of our model, the source and the sink. That means orders are released into production by the source lock. The orders are waiting in the buffer until the processing stage is idle. So we can specify the capacity of the processing stage. Assume that the capacity is in the beginning 1. So 1 unit can be processed at a time. That means when this processing stage is producing, then all the following orders have to wait in the buffer until this processing stage is idle again. After the item is processed, it has to wait in the FGI until the due date is reached. And then the model boundary has been reached. You can assume that the customer, for instance, takes the product immediately out of the FGI when the due date has been reached. So, and now I would like to show you in Anylogic the final product, what we are going to model in this course. So here you can see the Anylogic model. Here are all agents defined. So this is the Explorer view in the project view. In the middle area, you can see the coding, how I have arranged the blocks. I have just opened the main agent. Now we can see the model. What you can immediately see, you can identify the same structure I've already presented. So you can see the source generating the orders, the order queue where the orders have to wait until the processing station is idle again, and the FGI delaying the orders until the due date is reached, and the boundary of the simulation model, the sink. Here we can see some statistic, what we are going to measure. So we are going to measure the average WIP, the average production lead time, the average tardiness of the system, the average FGI lead time, and of course, service level. We are using statistics element, are indicated by stat WIP, histogram for the production lead time, and histogram for the tardiness, again a histogram for the FGI lead time, and a histogram as well for the service level. And we are also going to visualize some of the key figures as indicated here. So now I'm able to start the model. The applet is now generated. Anylogic is a Java-based system. So the Java applet is now going to be generated. And you can see here now the model. I can run the model. I can visualize the simulation time, and then we can see how the orders are released into production. Right now, order is being processed in the processing station. Orders are arriving in the order queue because the processing station is idle. Now, one order is waiting in the FGI until the due date of this specific order is reached. Now we can run the model as fast as possible. This is one of the advantages of simulation, so that we don't have to wait until the time has lapsed, so we can run the model as fast as possible. You can see the runtime is now 6,000 minutes. Now the key figures have been calculated. Yeah? Let me enlarge that a little bit. We can see the average of the WIP is 10.191 pieces. If you're interested in more details, you can also see the minimum WIP, the maximum WIP, the mean, and how many data points are used for calculating the average. The same appears for the histogram, for the production lead time. So the average production lead time for this simulation is 102.399 minutes. We can also have a look on our charts. In this chart, the WIP metrics are visualized. We can see in the black line the average WIP. We can see the current WIP in our model, and we can see maximum appearing WIP at each specific time point. So in the end, the average of the maximum WIP is around, what is it? When it goes to the WIP, we can check it, it's 22. And this is 22 units per time. And the idea what we are going to do is that I'm going to introduce how we are going this model together. So I'm trying to base my explanation on the outline. Here you can see the outline. So it's a written documentation, step-by-step introduction, what we have to do to generate this one machine model, and especially for configuring the model, the specifications are needed. So there are specifications for the source inter-arrival time, the time between two orders, the amount of orders per arrival. So in this case, one order arrives at a specific time. Then the planned delivery time or customer required lead time means when does the customer needs its products when he has stated the order. Yeah? So he states the order, and then at that time we add 100 minutes to calculate the delivery due date. We need the capacity of the buffer and the strategy of the dispatching rule. In this case, we are just using first in, first out. And the capacity of the production step is 1. So the machine is only able to produce one item at the time. Then we also need the processing time, which is in this case 10 minutes. And the simulation time is defined by 6,000 minutes. So then let's get started. The first step, it's indicated, this is just as an advice, that you can open a Word document and then you can just mark the blocks you need for documentation. And then you can also give some further information. So that could be useful for the assignments and as well just for making notes. Let me show how that is working. So we are switching back to Anylogic. Then I'm going to open just a simple Word file. In the meantime, I'm going to what I'm going to copy. It doesn't matter. So I'm copying this model, ST central copy. And here is my document. Then I can include it with Control V, and then you have all necessary documents. So then we go back to Anylogic. When you have started Anylogic, you get a very warm welcome of the welcome screen of Anylogic. We can find tutorials. Of course, you can look off those tutorials, different modeling techniques, system dynamics, agent-based models, and what we are doing discretely. For now, I'm going to close it. Then the overview again appears, the project view, the main area where the drag and drop and the coding is happening, and then you can see on the right hand side the properties to adjust the blocks, and there you are able to enter code elements. So for now, we are generating a new model. We press on File, New Model. And the model name in my case is basis model. Make sure that you enter a location where you are able to find the generated model again. And the important part is the Java package. Whenever you are saving the model, means save as, then you can of course change the model name, but it is not automatically changed the Java package. The problem here is that you are only allowed to open one model with the same Java package at the time. So that means if you have saved as two different models, just having changed the name, but you did not change the Java package, then you're not allowed to open those two models at the same time. So my recommendation is, whenever you're going to change the model name, please change the Java package as well. And the easiest way is that the Java package goes along with the name of the model name. And we are also going to change the model time units. In our case, it's minutes. You're also able to change the model time after the step. So a new model is now generated. Takes a few seconds. And then immediately in the project view, the model is generated, and it immediately switches to the libraries. We go back to the project view. So we have here our main agent. So this is the basis where you're doing the modeling. And the main agent is opened as well, body here. So the first step we are going to do is to recreate the model. For that, we switch again to the palette. We search the process modeling library, which should most likely the first library available. We are also able to see all other available libraries for the PLE version. Nevertheless, we start modeling. So we need a source block, drag and drop it into the main agent. We need a queue. When you bring the queue close to the source block, then the connection is done automatically. For the next block, the delay, then I show you how it's working. If it's too far away, then you have to do it manually. It's a double click on the green dot. And then you make the connection with just a click to the enter port of the following block. And we need again a delay block. And the final part, system boundary, is a sync. And we are going to rename those blocks according to the outline. The source, perhaps I enlarge my model a little now, so that you are able to read it. So please click on the source. We are going to rename it to source with a capital letter. The queue is called order queue in capital Q. The delay block is renamed to process sing station with a capital S. The lay block, the second one is just FGI. So you can see a collision of the text fields here. So you can again just click on the block. Then you can select the text and you can move it beneath the block, and so it's readable again. The final block is called sync in capital S. So now we are able to run the model. So there are two options. You can run the model, meaning the model is generated, the Java applet is generated, and then you have the model within the Java applet, or you can just build the model, which is also executable with the button F7. So if I execute the model, then I just can see that the model has been completed successfully. So this is a short identification if there are some mistakes in the model. But on the other hand, we can, of course, run the model. Takes a few seconds. And then the Java applet appears. We have the model here. Orders are generated, but we do not know how the orders are generated. And finally, we also receive an error message, exception during discrete event execution. Please try to read all the error messages before you close them, because it's an indication what has happened. And it says here an agent was not able to leave the port root.source.out a specific time. So when I close it now, you can see a red circuit indicating that that agent was not able to enter the following block. There is a obvious reason for that, because the standard configuration of the queue block has a capacity constraint of 100 agents. And you can see here 100. So already 100 agents are waiting in this order queue. That's meaning the 101st agent is not allowed to enter the order queue. That's the reason why we got this error message. But it's also obvious because we have not configured this model so far. We have just used the standard configuration, and this is not really the function we have. So there is no arrival process defined, and also the processing process itself has not been defined so far. Even though there is no logic behind how the FGI is working. So we have to make sure that the logic now is transferred to the model. For that, we need parameters. So please go to the agent library, and then you can find the parameter. Drag and drop the first one in. This call is called PRR. So the abbreviation is good for searching your parameters, because when you do the searching, then all parameters are listed next to each other, and you are not getting confused to find the corresponding parameters. The first one is the arrival control space. And then you can see all possibilities you're allowed to enter in this field. And that's also the reason why we have used the abbreviation PRR. And now we go and search the arrival time mean. So one tricky part is we also have to make sure that the parameter has the right dimension, because a parameter can be an integer, can be a double, can be a character. Of course, in the beginning, you do not know that by heart. That's the reason why we can use the Anylogic help. So we go on help, Anylogic help. In the beginning, it might take a little longer because it's getting indexed. And now we search for the source. Click on the first one. then you see a pretty smooth description of the source and also all the parameters, how they are defined and what they are doing. So if we go now to inter-rifle time, you can see the default type is set to a double. So we set or make sure that the rifle time is a double. And we have already checked that because no mistakes have occurred. But if you have chosen the wrong type of parameter, then a mismatch error will appear. Then you get the, for instance, the message integer cannot be cast to a double because a double is requested. You might have chosen an integer, and then you get the message that something is wrong. So when we go to the order queue, we have already seen here the problem. So the standard configuration goes with 100 items capacity restriction. So we select here maximum capacity. In the processing station, we are going to link the processing time. So it's not good if my mobile phone rings all the time. So we are going to link here the processing station. And we enter here the parameter of the resource capacity. And then it's done. The FGI we are going to model in a later step. For the FGI, we need further information. We need at least a due date so that we know how long this order has to stay in the FGI. And until this due date is reached, then the order is transferred to the sink, meaning the customer can take the order out of the FGI. If you go back to the source, we can see that a standard agent is used. And this standard agent has the drawback that we are not able to enter new information to this agent. But we would like to have individual due dates. That means we have to generate a new agent where we are able to store additional information, such as the due date or the arrival time. It's also possible to store information about the product itself. What should we produce? Should we produce a mobile phone? Which type of mobile phone? So you can also get an identification number, see which final item should be produced. But this is not possible in the standard agent. So we need to execute further steps to generate a new agent for the orders. So therefore, we switch back to the process modeling library. In the beginning of the list, you see the agent type. We drag and drop this agent type into this model. And then pop-up pops up. Agent type name. We call this agent order. We generate the agent from the scratch. Next one. We want to have 2D visualization, then you can select whatever you need. Doesn't matter because we're not going to animate it. And now the important thing is that we generate the parameters of the order. So the first one is the attribute. I call those attributes ID. Next one is the attribute arrival time, capital T. We go to the standard configuration, double. Next one, attribute due date is again a double. Attribute time stamp 1. This is a possibility to make calculations. And we need a second one, attribute time stamp 2. And we can now click on finish. And this order is now opened as an agent in our main view. You can see all the parameters we have selected. When you have done a mistake, then you can delete this parameter, and then you can drag and drop a new parameter inside. You can rename it, set the type, double, integer, whatever you need. If you need further parameters, of course, you can extend the parameters according to your needs. So, but the main message is, of course, we can see here the visualization object, which we are not going to use in this basic model. We can close it, but the main message is that we can see here in our project view the new agent order. And now we have to connect the simulation model with this new agent. So we go to the first block, to the source. We change the agent to order. And then a little tricky thing is you have also to check in the section advanced. There are, of course, two advanced section in Anylogic to make your life more complicated. So I have to move it a little bit on the left-hand side so that you can see it, so that my face is not disturbing it. And here you can see the second agent type. You have also to make sure that both agent types are selected to the new order we have generated, to the new agent we have generated to the order. We go to the order queue. We select in the order queue, or we check it, because now in the latest version, it's very convenient whenever you change the source, the following blocks also change the order type. Nevertheless, make sure that the queue block has a changed order, cold order. The same goes for the processing station. The delay block here under advanced also has already changed the order. The FGI delay block has the order. And finally, the sync. We can rerun the model. We have mistakes. That's great. So I can show you how you can see mistakes. And what happened here is type mismatch, cannot convert from double to int. And it also says where, especially here in the processing station. So the problem is that the resource capacity should be an integer, because there is only discrete steps of changes possible. 1 machine, 2 machines, 3 machines. So when you change that, then we can rerun the model. And we get rid of all mistakes. Model is running. And when I go to the simulation time as well, we can see every 10 minutes, so 19, 20, the second one has appeared. At time 30, the third order appears. 7, 8, 9, 10. So this is exactly what we would like to have. We have now a deterministic inter-arrival time. Every 10 minutes a new order arrives. And the same goes for the processing station. Every 10 minutes a new product leaves the processing station. 8, 9, 4. So now 4 orders have been processed in the processing station. We have not touched the FGI so far, so this is the step we are going to do now. So we are defining the due date based on the arrival time, and then we can model the FGI. So I'm closing that. And we go to the source block. We click on the source block. And yeah, perhaps I'm shifting my beautiful face to the other side, because then we can have a better look on the specifications here. So you can, of course, enlarge this one. And on the source block, we have now possibilities to generate code. So we are going to on exit. That means we are exactly generating code when an agent is at the exit block of the source block. So in the first step, we are going to define the arrival time. When we go back to the order, we have defined the attribute arrival time within the order. And now we want to give some information to this attribute. So back to the source. So agent. So this is the command to talk to the agent, and we are talking to the order agent. So agent dot, then we go for control space, and then we can see all possibilities we can select here. So we want to define the arrival time. We select the arrival time, and the arrival time equals to the time function, time brackets, and then we need a semicolon. The time function returns the simulation time at a specific point, and the specific point is exactly this exit point when an order is released to production. And now we can calculate the due date. Agent dot control space. We go for the attribute due date. The attribute due date. So you have two possibilities. We need the arrival time, which is stored in agent.attribute arrival time, control space, arrival time, plus, and the due date, the customer required due date, the customer required lead time is saved in the parameter due date horizon. So we add the parameter PIR, control space, due date horizon, semicolon. And now we just need to enter the due date horizon. The due date horizon should be 100 minutes. And now we have modeled more or less all we need for now for the source. So we have generated an own agent called order. This agent contains different attributes, such as the arrival time and the due date. And in the source, we align for each individual order its arrival time, and we calculate the due date. We can check if there appears mistakes, so we can go to the build model. It's just debugging. You can see the model completed successfully. Okay, you can't see it because there is the face again here. You can see here the model has been completed successfully. So this is good news. And now we can continue with the FGI. So we click on the FGI, and there is a strange standard configuration. So this delay block consists of a triangular distribution. We don't need this triangular distribution. What we need now is a delay when an order arrives early. So the due date is, let's say, 100, and the order has arrived at time 50. So we have to delay this order 50 time units until the due date of this order has been reached. So we have the due date information in the agent dot attribute due date, and we subtract the actual time at this point in time. That could work when the order is never delayed to the FGI. It could be the possibility that the due date is still 100, but the production system has delivered the order at time 110. And then, of course, no delay should appear because we are already 10 minutes late. That means we need now to observe your order. Are you on time? And you have to be delayed until the due date is reached, or have you already violated the due date and you have to go immediately to the sink? And for that, we need the max function. So we can again use max control space. Then we get information of the max function. We are using that. We can see two arguments, AA, separated with a semicolon, and then the second argument appears. Yeah? So we are going to do that. The first argument is the calculation of the delay time when the order is, so to speak, too early in our FGI. And then the second value is 0. So let's see what happens if the order is on time. So again, due date is 100, time is 50. 100 minus 50 is 50. The maximum between 50 and 0 is 50. So in this case, the order is going to be delayed 50 time units. And in the other case, assume again we have the due date with 100 and the order arrived at time 120. So 100 minus 120 is minus 20. The maximum between minus 20 and 0 is 0. So in this case, the order is delayed 0 time units, which we would like to have because this order is already 20 time units late and has to leave immediately the FGI with no delay. The next thing is we need here maximum capacity. So whenever an order arrives, it goes immediately to the FGI, so we don't have any capacity constraint in our FGI. Of course, reality sometimes behaves differently, and then we have to remodel that. But this is now assumption. The FGI has unlimited capacity. And then we also have to make sure that we are using here minutes. So the processing time uses minutes, and the source for the inter-arrival time uses minutes. So this is basically the situation where we can run now the model. Let's see if some mistake errors appear. Model is generated, no mistakes. And this is our final product. I can include again, of course, the timeline. We at 20, the second order arrives. And at time 20, also the first order is going to the FGI. And if you click on the FGI, you can see, let me stop it. We have now 28 minutes and 82 minutes. This order has to wait. So for this circumstance, the order has to wait exactly the time difference between the due date and the order, which is 90 minutes. Why 90 minutes? We can check that immediately. If I stop it again, I'm going to rerun it, because at time 0, no order has arrived. The first order in our system, according to Anylogic, is arriving at time 10. So Anylogic has now released the first order. At time 20, the order is processed. And is now in the FGI. And here you can see the delay time of 90 time units. At time 10, the order is generated. We add the due date horizon of 100. So the due date is 110. 110 minus 20 is 90 minutes. Great. So the model is working. But what we are missing now, unfortunately, are all our key matrices. So we have to include measurements. This is our next step. So I'm moving again to the right side. So next step, measuring key matrices. So we change to palette. And we need variables now. So the first variable, again with the abbreviation var, and the name is whip. Next one, variable, not car, variable would be nice. Production lead time, capital L. Next one, variable tardiness. Next one, variable FGI, capital L, lead time. So then I need a little more space here. The last one is the variable service level, capital L. Of course, just the first L. Service level. Good. And now we need live within our key matrices. So we start with the work in process. The work in process is the area between source and FGI. So the blocks, order queue, and processing station are in this circumstance defining the work in process. So we have two possibilities to start, because according to Anylogic, it does not make any difference if we are going to model it on the exit of the source or on the enter of the order queue. But what we have to do, basically, whenever an order is released into production, we have to increase WIP by 1. And whenever an order is leaving the production, we have to decrease the WIP by 1. Because the assumption here is 1 order per arrival is released to production. So in this case, I'm going to the order queue. Order queue, where are you? Here are you. On enter. And I increase now the var WIP. Okay, control space. Searching for the var WIP. And ++. And I've seen now that the var WIP is defined as an double. It should be an integer because the WIP can only be 0, 1, 2, 3. So only discrete values are possible for the WIP. Of course, the average WIP can be or is in the end a double. Because the average WIP could be 1.25, for instance. Good. We have increased now the WIP, and now we're going to decrease it. So I'm doing it at the exit, on exit. of the processing station. Here again, you could also model it on the enter block of the FGI. So I'm going here on the exit, var vip minus minus. And then I'm going to start the model again so that you can see what's happening. So where's my Java applet? That takes long today. Here it comes. And we can run the model. And we can immediately see, if I pause this model, one order has been released. We know that already, that will happen at time 10. No order, of course, is waiting in the order queue, but one order is waiting in the processing station because it's processed for 10 minutes. We continue at time 20 or slightly after time 20. Stop. So I selected now 20.60 minutes. 2 orders have been released to production, whereby one has already left production. So again, we have the situation, only one order is in the whip. So this is exactly what we would like to have. And now the interpretation of this whip variable is the actual whip at time 20.60 minutes. And there, the actual whip is 1 unit. But in the end, we're interested in the average whip. Perhaps we're also interested in the maximum whip so that we can define the space which is needed in front of the machine. That means we have to continue modeling. So we are going to select the palette analysis. And then you can see the statistics. So we take the statistics. The abbreviation is STAT, S-T-A-T, VIP, capital VIP. And then you have to make sure to select continuous, because the VIP is time dependent. You have to transfer the information of the value itself. So increase by 1 or decrease at the processing station by 1. And we also need to transfer the information and which time this change has to happen. If you go back to the manual simulation, there we also had the scenario where we were calculating the average whip. And it's a difference if the whip increases at time 1 or increases just 1 period later. That will immediately influence the average of our whip. Then we make the complicated one, but this is the huge advantage of discrete event simulation. So we do the update of the statistic element because we already know where in this process the whip has to be updated with the statistic element. Because whenever we increase the whip or whenever we decrease the whip, we have also to update the whip by ourselves. Of course, it's possible to update that automatically, but if I go back, then the disadvantage is here that we have to define the recurrence time. Meaning, in this case, every minute, Anylogic takes a look on the variable whip. What is your what is your value? And then Anylogic is doing that every minute. And so we are generating a lot of data, which is not necessary because we know exactly when the whip is changing. And the whip changes when an order arrives. And the idea of discrete event simulation is that this time points, so this time point, an order enters the order queue, triggers events. And the event is, please update the statistic element. That means we are reducing data because we do not use update data automatically. We go for do not update automatically. So we are going to do it by ourselves. So we go to the order queue on enter. So we talk to the statistic element by stat whip dot control space, and then we go for add. And here you can see we have to transfer a value and a time. The value is easy. This value is stored in the VAVIP. And the time is much more easy because it's the time function. So we can copy that one. We can go to the processing station and add the same line after VAVIP minus minus to update the statistic element. And then we run again the model. Let's see if it's getting faster. Java applet, where are you? Here is the Java applet. We extend it to see the time. Model is running. Average whip is 1. We can run it as fast as possible. And we can see the average whip is always 1. Now we have achieved a new problem because we have not defined so far the ending time of our simulation model. We can do that, of course. If we go back to project, we select the simulation, and then you can find the model time. The model is now never stopping. This is not useful. So we stop the model at the specified time, and this is 6,000 time units. We also can check the randomness, and we check that the fixed seed, the random generator, has the seed value of 1. So we are always taking the same seed values for our random generator. In this case, it's not needed because for this basis model, just deterministic values are applied in this model. So we start the model again. So model is coming. I can run it now as fast as possible. And we can see in the end of the 6,000 time units, the average whip is 1. We can also check the mean is 1, which we already could see outside. The minimum value is 0. The maximum is 1. And now you can discuss for the assignment why 1,199 units have arrived for the calculation of the statistic whip. I close it. So, and the next point we are calculating is the production lead time. So the production lead time is the time an order needs until it's processed. That means it's the time between the source and the enter block of the FGI. So the order queue and the processing station are the 2 blocks involved in the production lead time. The FGI is needed for the FGI lead time and only the FGI block. So that means we go to the processing station, click on the processing station, and on exit, we are calculating the production lead time. We store the production lead time in this beautiful variable var production lead time. So variable production lead time, here it goes, equals the time function representing when the order has left the processing station minus the arriving time of the order. And this arriving time has been stored already in the order agent in the attribute arrival time. So agent dot control space arrival time semicolon. So perhaps it's a good idea to move again to the other side. And I enlarge the text. And now we transfer the variable production lead time to an histogram. That means we change to palette. We search for histogram. And we insert the histogram. We rename it to histo production lead time. We go back to the processing station. And now we add the variable production lead time, where we have stored production lead time, to the histogram. Histo, control space, production lead time, dot. Then we can again hit control space. Add. We add the variable bar production lead time, control space, and then it's done. We can check it. We run the model. Here comes the applet. So we increase speed, double speed. For example, the mean is 10, which is somehow obvious because we have no stochastics involved in this model, and the input and the production process itself are aligned. If you run it as fast as possible, then you can recognize the mean production lead time is 10. You have a closer look on it. The mean is 10, the minimum is 10, the maximum is 10, resulting in no confidence interval and no deviation. So then I'm going to explain to you how we can calculate the remaining two key figures, the FGI light time and, three key figures, tardiness and the service level. Therefore, I'm going to open my model. I increase the view. So for the tardiness, FG lead time and service level, you also have to use histograms. And then we go again to the FGI. And on enter, after we have calculated the production lead time, you can find here the block how I calculated the FG lead time. So again, I'm using the max function, calculating the due date minus the arrival time, which is equal to the circumstance when an order arrives too early and has to wait in the FGI. And then the max function takes the maximum of 0, indicating that an order has been delivered too late and has already violated the due date, therefore the 0. And the other part is the due date minus the time function. Then I'm transferring it to the variable FG lead time, and this variable is transferred or added to the histogram. And in the sink, there you can see the calculation for the tardiness. So again, the tardiness, if we are late, then tardiness occurs, yeah? That means we are calculating the time when the order arrives. So perhaps again, an example. So the order has a due date with 100. The time when the order arrives in the sink in the customer is 120. So we have 120 minus 100 equals to 20. And the maximum of 20 and 0 is 20. So in this case, the tardiness is 20. And the other case, if it's too early, due date is 100. The time is 50. Then what happens? Time is 50 minus the 100 is minus 50. And the maximum of minus 50 and 0 is 0. That means if we have no tardiness, then the 0 is taken by the max function. Then we transfer it to the variable tardiness. This is added to the histogram. And then we have calculated the average tardiness, the minimum tardiness, and the maximum tardiness. Finally, to the due date. For the due date, an if statement is needed. So we question in the first statement, is the due date minus the time greater or equal 0? That means the variable or the service level for this specific order is 1. So we have delivered the order on time. The else statement means the service level is 0. And we are saving the 1 and the 0 to the variable service level. And then we add the 0 or 1 again to the histogram. And then the histogram takes the average of all entries in this histogram. And then we have the average service level for our production system. The final step, which I would like to introduce you, are the plots. For instance, a plot. You can find the plot again in palette. You go to analysis, and then you take the beautiful time plot. You can rename the plot. And in the time plot, you're able to add data with the plus, and you can delete them with the minus. So for the time plot, what I did, the title is, for instance, the current WIP. The current WIP is illustrated in the variable WIP. This is the WIP at a specific time. For the maximum WIP, we take the statistic element, here statistic element. We use for the statistic element the max function, means dot max brackets, and in return we get the maximum WIP up to the point in time. The same goes for the average. So we select or we type in the title, the mean WIP, and the value is calculated again, your statistic element WIP, stat WIP dot mean brackets, and in return we get the mean value. For the production lead time, procedure is the same. For the current production lead time, we take the variable. For the minimum production lead time, we have to question the histogram. That means we call the histogram histo production lead time dot min brackets. For the maximum, we question the histogram production lead time max. It is also possible to return the mean. The same is done for the FGI lead time. Yeah. What you have to set for all plots is again data update. This again is done not automatically. Do not update data automatically. So we take care about the update of the chart because we know when we have to update, because whenever, for instance, the WIP increases or the WIP decreases, we have to update. Whenever an order leaves the WIP, we have to update the production lead time. Whenever an order is finished, we can update the service level and the tardiness. So you have to make sure that to visualize all possible points within your histogram so that you get your curves. If there is two less points selected, then you just get a snapshot of the last of the last stored data points in the data set in the statistic element or in the histogram. And now we have to take care about the update. So when we go to the WIP, example is the WIP, and we are calculating the WIP, we calculate or transfer the data to the statistic element. And this is exactly where we also have to update the plot. So in my case, the WIP plot is called plot WIP. And then we just use the function .update data brackets. And don't forget the semicolon in the end is a requirement of Java. And we have to do it as well when we deduct the WIP. And in this case, I'm doing it on the enter block of the FGI. So again, var WIP minus minus. We transfer the var WIP to the statistic element, and there we are updating the plot WIP. Here you can see that how it works for the histograms. For the histograms, I'm updating the plot production lead time, again, .update data. And for the histogram, because I've used two histograms here, I've used a plot for the production lead time so that I can visualize the lead times itself. And then I'm also transferring a chart histogram production lead time. That's the reason why I need two charts to update for the production lead time as well for the FGI lead time. And you can play and invest a lot of time to generate fancy charts, because you can see the standard chart looks somehow strange. You can change the background, you can change the color, you can change the area, the color of the area below the function. So you have a lot of possibilities, but it needs time to generate a beautiful design for your plots. Thank you very much for listening, generating the one machine model. Good luck. And if you have questions, don't hesitate to send me an email or during our Q&A session.